Hi, my name is Caroline Zur, and this is my lab on constant velocity. The purpose of this lab was to observe an object in motion at constant speed and direction and to construct a model that explains these observations using the momentum principle. The momentum principle, or Newton's second law, states that the net force acting on an object is equal to the object's mass times its acceleration. In this lab, we compared time and position data that we obtained by rolling an object with the expected time and position data of that rolling object that we found using a model given by the position and velocity update formulas. For my results, both the observed and expected position versus time graphs were linear, meaning that there was constant velocity in both, and the slope of each graph was similar, but the slope of the observed position graph was slightly greater than the expected position versus time graph. The main physics idea in this lab was Newton's second law, which again states that the net force equals mass times acceleration. If we rearrange and integrate this equation, we get a final equation, which is the velocity update formula, which states that V final equals V initial plus the net force times delta t divided by mass. If the net force is zero, or the forces are balanced, then the final velocity is equal to initial velocity, and therefore the velocity is constant. The velocity update formula can also be applied to momentum by applying both sides of the equation by the mass. We obtain that the final momentum equals the initial momentum plus the net force times delta t. We can also obtain the position update formula, which states that final position equals initial position plus average velocity times delta t. Why is this important? Well, when the forces are balanced, we can predict the final position and velocity of an object based on the initial position and velocity. In my experiment, my system was a blue water bottle, and the surroundings were everything else, such as the room, the floor, the earth, and the gravity, and me. The initial conditions were that the water bottle was at rest on the floor. Here's my experimental procedure. I set up the camera, placed the water bottle at rest, lightly pushed the water bottle across the room, and analyzed the video using Tracker. Here's a screenshot of my Tracker data and video. For the coding, I started with the basic code provided in Canvas. I first edited lines 35 and 36 to the initial position and initial velocity data that I collected during my experiment, as shown below. I edited line 49, changing t is less than 2.0 seconds to t is less than 1.0 seconds to match with my experimental time frame. I then edited line 49, changing the net force vector from 1, 1, 1 to 0, 0, 0, as shown below. This was important, as in the lab we are assuming that the forces are balanced in order to predict the object's position after 1 second at a constant velocity. I then edited lines 58 and 60, inserting the position update formula and the velocity update formula, again shown below. These steps were also important, as the model used these equations to predict the final position and velocity based on the initial conditions that I provided. Here are my models from coding. On the left is my position versus time model, and on the right is my velocity versus time model. Here are my observed versus expected results. As you can see, the experimental position values, shown in blue, are very similar to the expected values from the model, shown in orange. This is due to Newton's second law, as the initial velocity should equal the final velocity when the net force is zero. However, the slope of my experimental position values is slightly greater than the expected. This is likely due to error. The experimental velocity was greater than the expected. Sources of error may come from the assumption that the net force acting on the system was zero, even though there could have been unbalanced forces. Some of the possible unbalanced forces include friction and gravity. If there was friction, then the experimental velocity may have been smaller than the expected velocity. However, if there was an unbalanced force due to gravity, which could have been due to an uneven ground, then this would explain the experimental velocity being greater than the expected velocity. What if? What if when you analyzed your video data in Tracker, you made a different choice of the orientation of the axes? Changing the orientation of the axes would only change the results in the sense that both the direction of the object's velocity and the sign of the position would change. However, the magnitude of the velocity would remain the same, and therefore the analysis and conclusion would not change. If the axes were flipped, then the water bottle would have moved in the negative x direction and the velocity would be negative. However, this does not change the magnitude of the velocity. What if? Is it possible to say how many pushes and pulls are added together to give the net force of zero in the case that you observed? The answer is no. The number of forces acting on the object that create a net force of zero on the system can range from very few to very many. There could be a case with only two net forces, such as an up force and a down force. However, there could be forces in every direction, and therefore we cannot say exactly how many are acting on the system. Thank you for listening to my lab.